Hey folks, welcome to the Plugfest 2024 again. This is for the use case number 2, device routing. And what's unique about this opportunity is that, again, well, first off, my name's Joe Siriani. I'm a network design engineer with Aviat, formerly 4RF. And what's neat about this is that Aviat had the unique opportunity to attend a few days at Evergy's downtown Topeka GO office and test on-site with live RAN and core equipment. So all the testing that was performed for this device routing topology was on their live core. We spent about 3 days in August performing testing. We really appreciate Evergy, who provided tons of resources for us there, some great point of contacts. We had a good time, and I really appreciate it. So, and we certainly appreciate them being this year's sponsors for the event. So for device routing, Aviat has chosen, and guys, I'm not going to stay over here. I'm going to probably walk around a little bit here. Aviat has chosen to use something called DMVPN, Dynamic Multipoint VPN, keeping in mind some of the requirements for the device routing testing and topology was things like regulatory compliance. When you hear that, think NERC-CIP, FERC-CIP, any kind of critical application, we're looking to really secure that data over this network. We had to keep things like reliability and redundancy, things like safety and security, and of course, we wanted to implement tons of routing and segmentation techniques for this scenario. So on the right screen here, I'm not actually mirroring. I'm going to keep this static diagram up. This was actually the entire lab I created for this scenario. And so there's a bunch of stuff going on. I'm going to leave this up here so you guys can reference it throughout the entire presentation, and the slide deck will be over here as I continue to talk and go through this. So what we did was, to meet those requirements, we did, again, the DMVPN setup. If you notice on the top part of the diagram there, this is what's called the hub and spoke topology, all right? We've got dual hubs, not even just a single hub, a dual hub for redundancy on the left-hand side, and then we have the mesh Anterix Band 8 network in the middle, talking to 6 remote sites, aka spokes. All right, this is your hub and spoke topology. So think point to multi-point from a hub to the remote's perspective. All right. We then threw in some extras there. Actually, before I even move on, the mesh in the, again, this is a complete dynamic mesh of tunnels. All right. So they're not. Did I lose the mic? Oh, I got it. They're not just regular GRE tunnels. They're GRE tunnels, but they're fully encapsulated in something called IP security, IPsec for short. Okay, so they're fully encrypted. They're also created dynamically, which we'll see as we go throughout the slide deck how we did that. And they create this unique mesh where both hubs know where all 6 remote sites are, and all 6 sites know where both hubs are at any given time due to this topology and configuration. Once we got that mesh up, we then leveraged a dynamic routing protocol. There's a few to choose for interior routing, and we chose the protocol OSPF, okay, Open Shortest Path First. And what this does and how it benefits utilities is if anything were to happen to the topology, something were to break or routes were to change, a dynamic routing protocol is going to reconverge very, very, very quickly, hands off, right? We don't want to sit here and start creating all these single point-to-point static routes, right? This is a topology of 6. If I had 50 devices as remotes, what if I had 100 or 1,000? I'm not going to sit there and log into each hub and go, to get to this site, go here. To get to site 2, go here. To get to site, I'm not going to do that. I'm going to configure a dynamic routing protocol on each of these devices, and they are going to share what routes they know with the peers they've created and learned, right? So hub 1, hub 2, they're going to share their routes with all 6 remotes, and likewise, all 6 remotes are going to have a similar configuration, and they're going to share the routes that they have on their LAN side, which the SCL devices are connected to, and they're going to share them with the hub, and everybody's going to learn those routes dynamically. They're going to exchange databases, right? We then sprinkled a little something called VRF on this. So in addition to the mesh that you see going on, the hubs talking to the spokes over a dynamic mesh with a routing protocol over it, very busy. We have something called VRF occurring here. So between hub 2, wish I could use my laser pointer, between hub 2 on the left and spoke 6 on the right, the furthest device to the bottom, VRF stands for virtual routing and forwarding, and what that is, it's a virtual instance of the physical chassis. So Hub 2 and Remote 6 have these VRFs created. Just think a separate virtual instance of that router. It's pretty cool. Each virtual instance of that router, in addition to the default, gets its own ports, its own routing table, its own CPU cycles. It is a completely separated instance of the Aprisa router being used up there, all right? And then we did all kinds of crazy stuff. So between that virtual instance of Hub 2 and Remote 6, we threw a tunnel over that. Over that, we created a couple of VLANs for segmentation to keep traffic at layer 2 separate. So you see the two laptops that are pink and teal there. They're showing an example of keeping traffic separate at layer 2. So again, think critical data like NERC SIP, or maybe transmission versus distribution traffic, right? Point is, we don't want any traffic from one VLAN leaking over into the other. And we're doing that with virtual LANs over a virtual tunnel over a virtual instance of the real thing. And I'll dive deeper into that. So just to kind of look at a little bit closer, I know it's kind of hard to see the diagram over there. Just focusing on that mesh again. The black addresses in each of these boxes, those are what's called an MBMA address. Just think that is the physical address. Think SIM card when you hear that. MBMA equals SIM card, all right? So that dictates the physical path. All the SIMs can talk to each other over the Anterix network. And then the orange addresses, those are the tunnels that were created over the physical path. The hubs know that mapping is called an NHRP mapping. They both have a mapping in their database that says, I know all the physical paths to those remotes and the tunnels, the dynamic secure tunnels I built over that path to everybody. If you were to rip one of these guys out and drive 2 miles down the road and plug him back in, he only needs to rejoin the cell network, and he's reconnecting back to that mesh, and the hub is moving on as normal. There's a couple of extra IPs there. They're just like loopback addresses, things that allowed us to prove we're reaching the LAN side of things. You're going to see how the routing protocol kicks in and basically allows us to learn all these routes. Again, just a little more zoomed in logically to that VRF. So between Hub 2 and Remote 6, there's a complete separate thing going on in addition to that mesh up there, just for the device routing scenario to show the flexibility of what a topology like this can do for utilities, all right? So this is while the previous slide was a logical view, this is actually the physical view. So those two devices, the two boxes up top with the black text in them, that is the physical chassis. That's the regular VRF, the default VRF. If you were to log into the router, what ports are there, the CPU, all that, that's the default VRF as is, basically. We added the middle virtual outside VRF to link these two routers virtually, and then through that created the green box, or where the green text is, another VRF called VRF inside. That's virtually linking the LAN side of both routers together. And then we took a physical Cisco switch for port density and to create VLANs to separate layer 2 traffic. And we stuck a laptop pink in VLAN 30 and a port in the switch in VLAN 30. And the green text laptop is plugged into VLAN 40. They are remaining separate throughout that path over that virtual instance. So to give you a better idea of what that VRF looks like, just think of this diagram here. It's a physical chassis, but inside there are virtual instances of the chassis. If a downstream router were talking to this guy, he would not know he's talking to a single chassis. He would assume he's talking to 3 different routers downstream or upstream. It's pretty neat, right? For our testing, you can see some of the equipment here. We had, I believe it was a 12 RU rack. You'll see the 2 hubs you saw in the diagram. They're up on top of that rack, hub 1, hub 2. We've got the 6 remote spokes sitting on a DIN rail in the middle there. And we have a Cisco switch for port density and for management access sitting at the bottom of that rack. So these routers actually support fiber connections, and if you're not using fiber, you can throw a copper SFP in there. So those blue links are going into a copper SFP, and that's how I was gaining management into those boxes while they were talking over the Anterix network to each other. Just some more pictures here of the SIM cards getting ready to be inserted into each box. Obviously, when you start these labs, the cabling tends to be nice and neat, and towards the end, it's spaghetti. But as long as the lab commences and is successful, we're okay. Again, some pictures here of Evergy's cool lab at their GO downtown Topeka. Again, they provided us any and all resources we need, so it was a real fun time. and we really enjoyed it. Some more front shots here of the rack. The two laptops you saw in the diagram, they're sitting there on the right. So one is in VLAN 30, the other one's in VLAN 40. Some of the equipment that we used for the testing, we used the G&D SIM cards provided by Evergy. And the routers, of course, are Aviat Aprisa LTE routers. As far as the LAN devices go, behind Hub 1 and 2, these were your polling devices that were polling out to the remote spokes, the devices sitting on the LAN side. Hub 1 had an RTAC, a SEL RTAC sitting behind it. Hub 2 had a Novatech Orion LX. We had 6 spokes, but there were SEL devices sitting behind 1, 3, and 5 only for testing purposes. And so there was an SEL 651R behind spoke 1. Site 3 had a 2431 regulator control box. Spoke 5 had a 351S breaker relay box. And of course, all the RAN, cell site equipment, core EPC stuff was all provided by Evergy and its Ericsson equipment. So again, the unique opportunity here was this was done on Evergy's live RAN and core network at their site, not in a lab with the vendor. This was done on site with them, and we used a separate APN to keep our traffic separate from interrupting any production traffic, keep it safe. But it was on a live core and live RAN, which is pretty cool. Now, in case you missed it, you're not cool unless you have your own branded SIM cards. So if we start seeing you guys copy this, just know you saw it here first. Everybody's got some cool branded SIM cards with their name on it. We thought that was pretty neat. All right, so now we've got this big old mesh configured. We've got dynamic routing protocol configured over it. We've got all the routers talking to each other. They've learned their routes. How do we know that DMVPN is up and working? All right, there's a few ways to do this. We logged into the hubs. Up top, you'll see Hub 1, Hub 2. We ran a simple command, says show DMVPN. Show me what you know on a DMVPN perspective here. You'll notice Hub 1 and Hub 2, they learned 6 remote devices, right? That means 6 devices dynamically checked in, and you'll notice on the SA column, there's a 1 there. That means not only do they create dynamically a GRE VPN tunnel, it's a security association, which means it's an encrypted IPsec tunnel. So think of an encrypted, secure IPsec tunnel being built on the fly really quick. This is going to save utilities a lot of resources, time, most likely performance as well, because it's being done so quickly. So Hub 1 and Hub 2 both learned dynamically 6 different remotes that checked in with it, and it's now keeping a mapping of that, right? If we turn that around and go to the remote spokes, for example, there's 6, but we grabbed 1, 2, 3, and 4. We ran the same command. Notice the same thing. While the hubs learned 6 remotes, every remote learned 2 hubs, Hub 1 and Hub 2, right? We have full mesh redundancy here. Every hub, every remote rather, knows how to get to the LAN device sitting behind the hubs via either Hub 1 or Hub 2, should any of them go down. Likewise, they've got an SA configured. That means they've got a secure security association, a secure IPsec tunnel built with those 2 devices. We also want to see that mapping where I said you had the tunnel address mapped to the physical SIM card address, right? We ran the command show IP NHRP. Hub 1's up top, Hub 2's on the bottom. They learned the IPsec tunnels. 10001 correlates to Site 1, 10002 to Site 2, and so on for all 6. And you see the mapping here. In the type column, you'll see dynamic, which means we didn't statically configure this. They learned it dynamically. The remote checked in. We kept the mapping of it, and we learned they had a tunnel address at 10001 mapped to a physical SIM card address of 192.168.191, 10 for Site 1, 20 for Site 2, 30 for Site 3, and so on. So the hubs are fully keeping the mapping of the logical tunnel address to the physical MBMA address, SIM card, right? And they're all learned dynamically. The one local you see is its own IP address. He's 10.0.0.10 for Hub 1, 10.0.0.11 for Hub 2 on the bottom. A lot of dynamic, automatic stuff going on here. Likewise, turning it around, we ran the same thing. Show me the mapping from a spokes perspective. 1 through 6, how do you know? They see a mapping of 10.0.0.10, 10.0.0.11 tunnel address being mapped to the physical SIMs of the hub, ending in 192.168.191, 100 for Hub 1 and 200 for Hub 2. Okay? So now we've confirmed we got DMVPN up and running. Routing protocols exchanging routes. Everyone knows who has what routes thanks to that routing protocol. How do we ensure the routing protocol is working? We decided to use OSPF, right? Open Shortest Path First. That's a dynamic routing protocol that routers can use to learn routes from each other. There's something called EIGRP. There's OSPF. There's BGP. There's a bunch of routing protocols you can use. OSPF is very, very, very robust, dynamic. It's hierarchical. We do something called areas in OSPF. And they also do something called cost. So cost means they're going to find the lower the cost of the link, the faster that route is, they're going to prefer that path over anything else. All right? We ran the command show IP OSPF neighbors. What neighbors have I learned with this routing protocol? Notice Hub 1 and Hub 2 have learned all 6 remote devices. They're neighbors with the 10.0.0.1 through 6 tunnel addresses. Now they can fully exchange routes with each other and say, hey, I know these routes. I know these routes. I've learned this. Hey, this changed. Did yours change? Did anything change? They're going to exchange just those differences. It's all going to be dynamic, robust, and very fast. Versus you going static IP route, oh, something changed. Let me do all those routes. We don't want to do that. We want hands off, right? Less human error and more dynamic going on. So we got the mesh. We got the routing protocol. We're learning everything. Again, we mentioned these are secure IPsec tunnels. How do we know that? How do we know the data is secure from A to B or from hub to spoke and vice versa? How do we know what the encryption is being used? How do we know what the authentication is? This thing called Diffie-Hellman groups, which strengthens the keys being used to rekey tunnels all the time, right? That's what makes it difficult for third-party hackers to get in there because we're constantly refreshing and rekeying those keys. Bigger the number, stronger the algorithm. What if your security operations come to you and says, hey, you need to prove to us that the data you're sending is indeed being encrypted? How do we do that? So if we go into the router's UI, we see first and foremost up top all those tabs. The first 2 tabs are Hub 1 and Hub 2. The remaining tabs are spokes 1 through 6. This page is showing that a layer 3 GRE tunnel was created. So IP over GRE means a layer 3 tunnel. And we've got the address of 10.0.0.10 for that guy. For those familiar with tunnels, GRE tunnels are great. They just connect things and lands together, but they don't actually encrypt traffic. You got to add some kind of encryption mechanism to encrypt the traffic. So we're taking that GRE tunnel and we're sticking it inside an IPsec tunnel and making it real secure. The next tab over, oh, sorry, this is previous LT1. So the first one was the hub. The second picture is one of the spokes, spoke 1. Showing his GRE tunnel, again, 10.0.0.1 for site 1, 10.0.0.2 for site 2, and so on. And what we did was in the IPsec tunnel tab, so you just saw the GRE tunnel that was created. Now we wanted to create this IP security profile, stick that little tunnel in this secure IPsec tunnel to make sure our data is encrypted. This tab is showing that we not only do utilities have the ability to encrypt the GRE traffic, but they can get super granular and choose what traffic type is allowed over this tunnel. We're not just going to let anything over this tunnel because it defeats the purpose. Why would we allow any, right? We're specifically saying here we only want protocol number 47 to traverse this tunnel. What is that? That's GRE traffic. So we're saying you need to meet the criteria to take this encrypted tunnel over to the other side. We're only going to let protocol 47. And because of the half screen, you can't see the algorithms here, but we're saying only protocol 47, use AES 256, use SHA 384. These are all algorithms that secure the data, all right? So this tab is saying what is allowed to go over the tunnel. The next tab is saying, this is called your phase 1 in the VPN world for IPsec. This is saying, hey, buddy, do you want to be a tunnel with me? Great. Can we agree upon all these parameters? Can we agree upon what Internet key exchange version we're using? We're going to use Ike v2. What's the pre-share key? What's the password? You got the password to be joining this mesh? If not, you're not going to be peering with me, right? So very secure on a tunnel level by itself. If we scroll down, you'll see, can we agree on these as well? Can we agree on the encryption algorithm being used? Can we agree upon the authentication algorithm being used? That authentication algorithm says, hey, I need to make sure that the data being sent between these routers have not been altered in any way, shape, or form. The secure hash algorithms are going to do that for us. Then there's your Diffie-Hellman group. If we match on all sides and our parameters match and we agree upon all those parameters and our pre-share key matches, we're going to dynamically form a tunnel with that guy. So now we got our GRE inside the IPsec tunnel, Again, how do we prove the SecOps? We've done that. If we go to this UI's monitoring page, we see Hub 1 over here has set up 6 IPsec tunnels. So he's got a secure tunnel with spoke 1 through 6. The top part is that phase 1, it's established. The bottom part is that phase 2 that says, hey, what is going inside this tunnel? Notice these child connections, they've got GRE in parentheses over here, from that local LAN to that local LAN. So utilities can be in full control of not only the type of encryption and security being used, but what is allowed inside that tunnel as well. That was Hub 1, this is Hub 2. This is spoke 1. Likewise, the hubs knew 6 tunnels, right, because they're learning 6 remotes. Each remote's going to learn 2 tunnels, Hub 1, Hub 2. They're established, and they're installed. Prisa LTE 2, 3, 4, 5, and 6 all have an establishment, and they're sending that GRE traffic successfully through the tunnel. So how do these remotes know where that hub is? How do you know to get there in the first place, right? Like I said, you can take one of those spokes off a pole or wherever it's at, drive it 2 miles down the road, put it back up on the pole, it's going to dynamically check back into that mesh. How does it do that? If you look at the configuration here, this is the CLI of the GRE tunnel itself. The 2 line items highlighted show IP, NHRP, NHS, next hop server. NHS is a fancy term for the hub, right? We're telling each remote, hey, your hub is at the tunnel address 10.0.0.10, which is mapped to the SIM card 192.168.199.100. We've got a second line item there for the second hub. What does that mean for utilities? It means not only can you use multiple hubs, but we can throw a 3rd hub in there, a 4th hub in there, right? We can do co-located devices in the data center for the hub. We can do 2 devices, hub A1, A2 in data center 1, and maybe hub B1, B2 in data center 2. We can have 4 hubs if we want. We only need to stick the other 2 line items in there, right? This is an extremely robust, dynamic mesh, all right? Knock down hub 1, we're going to go down to hub 2. Knock down hub 2, we'll go to 3. We'll go to 4. You can add as many hubs as you want. So here's the real test, right? We did all this. Again, when we met with Evergy, we sat there. We had like 3 full 8-hour days of testing. Every single thing was fully documented. There are probably 100 screenshots. There's probably about 8 to 9 gigs worth of video. Obviously, we can't all fit it in a 40-minute presentation. So I'd urge if anyone wants to see those tests in their entirety, come by the Aviat booth and be glad to play them for you, all right? I did, however, leave one video in here for the sake of time. It's the test where we're going to practice the redundant dual RAN redundancy mesh here. So we're going to run a test that we're going to sever connectivity from hub 1 to spoke 1. And we're going to do it in 2 different ways. We're going to sever cellular. And what we want to see is when that connection is severed, do we still have that secondary path? Does spoke 1 have that secondary path to hub 2, right? That's going to be cellular via yanking a antenna cable, right? Then we're going to do a second test, which is going to be a physical connection failure. The LAN devices that are polling the remote SEL devices, it was a Novatech and an SEL box in the head end, we're going to yank the cable from hub 1's device between that device and the router it's plugged into, hub 1, right? So we're going to yank the SEL cable out to hub 1 and see how that responds. Or do we still have a data flow then going to device, or hub 2 rather, right? Excuse the attire. We were told to be comfortable at Evergy's lab, and that's what we did. So, hope you guys can hear this. Where's my trusty tech guy? I trust sound is up. That's good.
All remote spokes have access to both hub 1 and hub 2, and the polling devices behind them. And so we're going to perform a test where we're going to simulate a failure a couple of ways on hub 1 and show that traffic is still traversing hub 2's link out to all the remote spokes. So for this example, if you look here, Joe, we're going to use remote spokes 1, 3, and 5, which have SEL devices on the LAN side. And I'll let Clayton explain which devices we have at the hub 1 and 2 routers and the 3 LAN devices for the test as well. And then we'll go ahead and commence the test.
So for hub 1, we have an SEL RTAC, and then hub 2, we have a Novatech Orion LX.
Both of them are talking DMP3 protocol to 3 different outstations.
We have device 1's a SEL651R, device 2 is a 2431 regulator control, and device 3 is a SEL351S breaker.
So if you come over here, I've got a test. I've got TCP dumps going on. And what we're looking at here is this big box here is hub 1's device, and this box here is hub 2. And I've got spoke 1, 3, and 5 in the background. I'm hiding 3 and 5 since we're really focusing on spoke 1 right now. And what this TCP dump is like a live Wireshark. We're analyzing the GRE tunnel interface. And right now what you're looking at is, you'll see a source of 192.168.10.10 reaching out to 192.168.110 on port 20,000. So we're seeing that traffic between hub 1 and device 1 hanging off spoke 1, going between hub 1 and hub 2. And then we see the responses and the traffic likewise, another TCP dump going on Aprisa LTE router 1, monitoring the same thing. Its focus is monitoring host 192.168.110, which is directly on its LAN side. So now we're going to go ahead and simulate a failure here in a couple of ways. The first way we're going to do is we're going to yank the antenna cable from the primary hub 1 device, simulating a cellular failure, and we're going to watch the conversation still occurring between hub 2 and the remote spoke 1 LAN device. So I'll switch places with Joe here. I'm going to yank the cable to hopefully sever cellular here on the hub 1 box. And right away you see there's only one-way traffic, 1010 trying to reach out to 1, but we still have a flow here on hub 2. So he's still talking. I'll go ahead and restore the cellular on hub 1. And we should see that conversation resume shortly here. But note that we still have that flow of traffic being collected at the head end on hub 2. So now we've restored. We see 10, which is the polling device behind the hub, reaching out to 1, and a full SCADA conversation occurring here. Right? Port 20,000 still flowing. And so we're back on both devices simultaneously. And now we're going to perform a second failure, and this time instead of cellular, we're going to fail physically at the hub 1 location. So Clayton is going to yank the cable between the LAN device of the Aprisa router and the SEL box. All right, cable's been pulled. Same as before, last poll we see is 1010 reaching out, and that is it. There's no more conversation going on because the LAN cable has been severed, but note that we still have a conversation between hub 2's router and LAN polling device to spoke 1's SEL box as well. Because again, there's full-blown mesh redundancy here. Every spoke knows how to get to both hub 1 and hub 2 should there be a failure on one or the other.
All right. Back on? Can you hear me? Oh, there we go. So thanks to Joe McFadden, my trusty camera guy, during that trip. So as you guys can see, not to spend too much time on it, but between hub 1 and spoke 1, we failed that connection a couple different ways, and we still always had a data flow between spoke 1 to hub 2, right? Evergy still received their critical data, even though the hub 1 went down, all right? Something else, are we doing on time? Something else I'll throw in here that was pretty cool. We did this thing called DMVPN Phase 3, aka it's called spoke to spoke. There is kind of a rising use case here with certain customers where sometimes, by default, this mesh you see here, all the traffic, am I still on? Okay. All the traffic traversing the mesh in the middle there, regardless of where it's going, it's always going to go to the hub first, right? But there's some instances where utilities might have a critical application not behind the hub in the data center. Maybe that application is sitting at another site, another data center, or another substation, if you will. So maybe the device at spoke 1 needs to get to something behind spoke 3, 4, 5, or 6, right? Not the data center, not the main hub. It has to get to behind another spoke. So with a few extra commands on the hubs and the spokes, we can do this thing called Phase 3 DMVPN spoke to spoke, where basically a dynamic or an on-demand tunnel gets built directly between two spokes. That's pretty cool. So what happens is some data from the remote spoke goes into the hub, and the hub says, hey, I've got a better way to get to that site you're looking for. Update your routing table with this new route and go this way from here on. The remote spoke will say, okay, and build a dynamic route through the public internet. In this case, private LTE. It'll build it through a set of different hops. And maybe what this does is it does two things for utilities. One, it reduces load on the hub, right? We've got 6 boxes here. What if we had 10,000 routers? We want to alleviate some of the load on the hub. When we do the point-to-point connection between spokes, we alleviate load on the hub, freeing it up for other resources. We're sending that payload directly between the two remote spokes. Only a few control packets are going back to the hub to let them know, hey, I'm still here, I'm still part of this mesh, don't count me out, but the main payload is going directly to the other spoke. When that's no longer needed, or the two devices are no longer having a conversation, being that tunnel was on demand, it gets torn down to save you resources because it's no longer needed. Only the tunnels to the hub remain up always as static tunnels. That's pretty neat, right? And even though they're dynamic tunnels created as needed between spokes, they too are also secure IPsec tunnels. They're not a different kind of tunnel. They're secure using the same algorithms that were entered earlier, which could be a security requirement on your part. So you want that, right? Last but not least, VRF. Again, this is a really cool technology. This is known as VRF Lite. This is that virtual technology. This is a bit of a better picture here where note the single chassis on the left's got 2 virtual instances created in addition to the default VRF. The standard router as is called the default VRF. We added a VRF orange, a VRF blue. We could add 100 VRFs if you want, right? We can create as many virtual interfaces and stick them in all kinds of VRFs. The guy downstream doesn't know, he's none the wiser, right? He thinks he's talking to complete separate layer 3 routers upstream or downstream. Notice here, what this allows utilities to do as well is we can overlap IP addresses. Notice all 3 of those interfaces in different VRFs, they're all using 192.168.1.1 on the left, going and talking to 1.2 on the right. Normally, a router will bark at you if you do an overlapping IP. If you have an IP address on one interface and try to put the same IP or an overlapping subnet on another interface, routers are going to bark at you and say you can't do that. Because of the VRF, the router will not bark at you because you've used these as 3 completely separate routers. Therefore, you can have a 192.168.1.1 in all 3 as long as it's 192.168.1.1 VRF blue, 1.1 VRF orange, 1.1 default, right? So very beneficial technology and very robust. Again, this is where the VRF was used. Getting the physical stuff out of the diagram here, just is all virtual here. The only physical things going on here are the laptops plugged into the switch. Everything else is a virtual logical connection occurring over those VRF instances. And the test was, again, we have video for this if you want to see it at the booth. We ran tests where traffic in the pink VLAN 30 was not allowed to talk to the blue VLAN 40. We kept that traffic completely separate, all right? So if you have some critical infrastructure traffic that just can't go out, this is how you'll keep it separate at layer 2. That's pretty much it, guys. I'll just do a quick wrap up here because I really want to, I want utilities to understand what the benefits are here to them. Again, scalability. With this type of topology, if creating hundreds of manual point-to-point links is your thing, fine. We don't want that. We want something that is scalable and that can grow, say, oh, I didn't know I've got to throw 50 more spokes out there next year. I didn't realize that. DMVPN is going to be your topology because it's very scalable, all right? You can just get a cookie cutter config. Once you configure the hub, you don't touch it again. You just configure cookie cutter remotes and you deploy them. It's going to save companies tons of time because it's going to be a rapid deployment of these devices, right? Use something like that in conjunction with some kind of a zero-touch or low-touch provisioning tool, and now you really got something going on here, right? We're going to alleviate load on the hub, right? We're going to send less traffic on the hub, freeing that guy up to speed up a bit, depending on how big your topology is, thanks to that spoke-to-spoke communication. There's going to be less configuration. Again, the hub is known as a set-it-and-forget-it kind of topology. Once we configure that hub or hubs, We let them go. We only configure the unique IP remotes, and we just keep deploying them. They know how to get to the hubs from there on, right? With this kind of topology, we're introducing WAN redundancy, right? Can't get to hub 1, let's go to hub 2. Even if 2's down, let's go to hub 3, hub 4. You can have as many hubs as you want in this topology, right? Obviously, we've enhanced security by using only the top-notch security protocols, right? You guys, your companies, your security operations can dictate what that is based on the regulations, or you know, we can use something like NIST recommendations, right? The National Institute of Standards and Technology. They've got recommendations that we can also use on the router, and if a company doesn't have any requirements, we often recommend that. Again, we have the flexibility, once the mesh is created, again, the flexibility of throwing a dynamic routing protocol over that. That's immense, because that's going to allow you to save tons of time by having the routers learn routes from each other rather than you going in there and physically, manually configuring every single point-to-point route. You're not going to do that when you've got 100, 200, or 1,000 remote spokes, right? Because if you did that, you have to do a route from hub 1 to remote 1 to 1,000 and go on the remotes and do the reverse route back. We're not going to do that, right? Again, eliminates configuring manual point-to-point links, as we mentioned. The VRF, again, we can leverage that. If you're familiar with VLANs at layer 2, VRF is the same exact concept, but at layer 3. Layer 3 virtual routers, right? I think I'll stop there. The rest I kind of mentioned already. But I do want to give some time for questions from the audience if you have any. I do want to end it on a slide here. Here we go. This is actually Evergy's live cell site on their building with drone footage. Excuse the sluggish video. It actually is really smooth on a Windows device. Can't trust these Macs they gave us here. But shots fired. But yeah, this is actual drone footage circling Evergy's cell site, their eNode B, up on the top of the building there in Topeka, Kansas. It's pretty neat. They got a really neat setup. I'll let that go. Any questions from the audience at all? I know I threw a lot at you, and again, we're trying to condense 3 8-hour days into a 40-minute presentation, so forgive me if I went over. If no questions, appreciate your time. You're more than welcome to come by the booth and pose any questions there. Aviat's over towards the front entrance there if you want to stop by and have any questions. Thanks, guys.